we are live. Hello, everyone. It's 3 p.m. in the beautiful city of Rotterdam, where we are about to begin our journey together. As you all know, today we are here for the launch of our latest product, the 20-mode quantum photonic processor. Well, let me tell you, this is not all. Who is QuiX? Why QuiX? What QuiX quantum technology can do for you, and how QuiX quantum technology is today tracing the path to build up the quantum future of tomorrow. We'll try to answer all these questions today in the next hour and a half. But before starting, let's have a look at the program. We'll start with our business case, QuiX Quantum. And then we have asked two of our academic collaborators to come and share with us their stories on how it is to work with our processors. So we'll have a first guest speaker from the University of Twente and a second from the Paderborn University. And last but not least, the product launch, the 20-mode quantum photonic processor. So we have a lot of things to talk about, and I think it's time to get the ball rolling, shall we? Ladies and gentlemen, welcome to QuiX Quantum second webinar. Now, luckily, I'm not alone today in the studio. Here with me, there are our CTO, Jelmer Renema. Hello, Jelmer.
Hello.
And our senior project manager, Jorn Hepping. Hello, Jorn.
Hello, Katharina.
Now, I don't know you guys, but I'm very excited about today. So we have a lot of things to talk about. One useful information about the Q&A. You can ask your question throughout the entire event via the chat that you can find on your screen. We'll try to answer all your questions, either directly in the chat or live in the studio. And if we run out of time, we'll get back to you right after the webinar. But I would say let's get down to business now, ladies and gentlemen. And I mean it literally. So, Jelmer, the floor is yours.
Thank you. So, my name is Jelmer Renema. I'm the CTO of QuiX Quantum, and I'm going to tell you something about what it is that we are doing and give you some information to place today's product launch in context. So, our mission statement at QuiX is to make the world's best quantum photonic hardware. And as you will see in our presentation today, this is what we have succeeded at. Who are we? We are a photonic quantum computing company located in the Netherlands, in Enschede. We are a spin-out of the University of Twente, and we have a growing worldwide network of distributors. We were founded in January 2019 with a pre-seed round of a local investor called Raft2Invest. Then in the summer of 2020, we picked up a seed round where the lead investors were Forward One and OostNL. And we are currently at 12 people headcount. The CEO, Hans van der Vleckert, myself, our CFO, 8 engineers, and our office manager. So you see the entire company represented here. So we at QuiX are market leaders in quantum hardware for photonic quantum computing. And photonics is a great technology platform to be doing quantum computing with for a few reasons. One of the reasons is that it's only one of 2 technology platforms which has actually succeeded in achieving a quantum advantage. So what does that mean? It means that it's only one of 2 platforms where a quantum device has actually succeeded in outperforming classical supercomputers at a particular given computational task. Other reasons why photonics is a great platform is that it's highly scalable. It has a very strong technology crossover with classical photonic technologies, and the core components, right? Photons maintain their coherence at room temperature, so you can operate your quantum computer, at least the core components, at room temperature. At QuiX, we lead photonics when it comes to quantum computing. So as I mentioned, we produce and sell the world's most advanced quantum photonic hardware. What does most advanced mean? It means both most powerful in terms of computational capabilities. It also means the highest performance characteristics in terms of the specifications of those components. And something that I'm particularly proud of myself is that we have succeeded in delivering on all of our technology milestones in a market that, let's face it, is known for occasionally overpromising what it will do. So quantum computing with photons is a near-term non-universal form of quantum computing where you use the position of the photons as an information carrier and where ultimately the computational power is set by the number of modes. A few proposed applications are machine learning, isomorphism, quantum chemistry, and so on. So our product portfolio at QuiX consists of essentially two things. First of all, the quantum photonic processor, which is the core component of a near-term quantum computer, where, as I mentioned, the computational power of this processor is set by the number of channels that you have, so the number of optical inputs. So this is our one product line. This is the one that we're going to be talking about today. The other product line is for NISQ photonic quantum computers, so near-term photonic quantum computers, where you can see a picture of our development bench there, where we use the processor as a central component, but where this processor that you see on the bottom left is integrated with photon sources and detectors. So then to say a few words about our QuiX quantum photonic processors. So a bit more than a year ago, we launched this product line with a 12-mode quantum photonic processor. This processor we will see back in the two academic talks that are upcoming, where you will see some ways in which our academic partners have used this processor. And today we are extending this line with a 20-mode processor. And I want to emphasize this is the most advanced quantum photonic processor in the world. Right? So what is being presented here today is really the state of the art when it comes to quantum photonic hardware. The key technology here is a photonic integrated circuit. So you see that here at the center based on silicon nitride waveguides. And it is really this component that enables us to reach, as I mentioned, the best specifications on the market when it comes to quantum computing and also a record size system. And this is reflective of our ecosystem approach. So we at QuiX are at the heart of a cluster of companies delivering low-loss solutions for photonics. We integrate all of these components when it comes to quantum computing, and this has enabled us to be faster and more cost-effective than our competitors. The fact that we can use this ecosystem to get the most advanced waveguides in the world for this application. On the commercial side, things are also going well. We are market leader, so something that I'm very proud of is that we have sold, or at least shipped 5 systems to customers and academic partners. At the moment, the Hungarian, German, French, and British quantum technology programs are using QuiX quantum photonic processors, which makes our processor the de facto standard for photonics in European national quantum technology programs. I'm also very proud to say that we were the first Dutch company to realize quantum computing hardware sales. So photonics is leading the charge when it comes to delivering the promises of commercializing quantum technologies. And QuiX is at the forefront of photonics when it comes to delivering those promises. Then finally, I want to talk a little bit about the customer experience. So what do you see when you buy a QuiX quantum photonic processor? So our customers at the moment are mainly academics and quantum technology startups who are trying to develop, let's say, applications, or in the case of the academics, do academic research using this quantum hardware. So what do you see? You see a plug-and-play system that comes completely shipped with the peripheral electronics and the software. So you as the user just have to hook up your photons and your detectors, and you can start doing quantum processing. The processor is entirely turnkey, so it comes pre-calibrated. Let's say the software knows everything that it should know about this processor. And just to showcase how high the technology readiness level of this processor is, installations can be done via remote access. So the picture that you see here beneath our logo is of the device that was shipped out to Hungary last week. And as I understand, it has been installed today entirely remotely. So this tells you let's say, how mature this technology actually is. And finally, the processor is upgradable with respect to the control electronics. So if you buy a larger processor and you already have the control electronics, you can swap out the processor with your existing control electronics and it will work. So what does the future look like for QuiX? We aim to expand our product range of quantum photonic processors to larger systems. So at the end of this calendar year, we will finalize our 50-channel system. The other thing that we will do is we will move this system, we'll start offering this system at different operating wavelengths. So at the moment, our system operates at telecom wavelengths. We will move this also to 925 nanometers to be compatible with quantum dots. And the other thing that we intend to do is to introduce new product lines, particularly cloud access for photonic quantum computing in 2023, and then finally universal quantum computation using photonics in 2026. And with that, I would like to conclude. As Katarina already said, questions can be asked in chat. Thank you very much.
Thank you very much, Jelmer, for these commercial insights. And I think we can now proceed with the rest of the program. So, as you might remember, if you watched our first webinar, there we launched our very first product. It was a 12-mode quantum photonic processor. Now, since then, in the last year, we have put in the market 5 of those working systems spread all around the globe. And today, we have 2 of our academic collaborators here to share with us how it is to work with the first generation of QuiX quantum processor. Basically the 12-mode quantum photonic processor. And the first speaker is the chair of the Adaptive Quantum Optics Group at the University of Twente and the director of the Center for Quantum Nanotechnology Twente, Professor Pepijn Pinkse. Hello, Pepijn.
Hello, Katrina. Thank you very much. So, it's my pleasure to show you a few things of the science we did with a QuiX processor here in Twente. Okay, so a little bit about my background, how I came here. I have a background in doing quantum optics with scattering media. In this kind of systems, like the sugar cube here, we did the quantum experiments having a single photon, 2 single photons in, photons coming out, real quantum experiments. Also for doing the quantum readout of physical unclonable keys. We did this with scattering media, with multimode fibers. And we started building quantum circuits with these random scattering media. And with that we realized that, oh, actually these media are, if you like, circuits for quantum information processing. Actually we were able to do some basic experiments with that. However, if you look at these scattering media, they work nicely. You can do some things with it, but they're fixed. They're completely random, and they're so lossy. And this is where the ultimate solution came around, namely an early version of the QuiX photonic processor. We did an experiment shipping one of these boxes to Oxford, to our collaborators there. And we did first multimode, multiphoton experiments in Oxford and wrote this first publication about this. This was the start of a whole series of wave of beautiful scientific results. I show there are at least 3 that I could show now, and there's more to come. But I will focus on one of them, which is the quantum photo thermodynamics, which you can find in the archive over there. Okay, so before introducing the experiment, I should say a little bit about the peripherals of the experiment, namely how we produce photons and how we detect them. Photons are produced in this experiment by 2 spontaneous parametric down conversion sources for the experts, which produces 4 photons where we typically use 1 as an herald. We inject them into our processor, which we got from QuiX. And then there is a number of detectors at the output. There could be up to 12 outputs connected to single photon detectors. But in this experiment, for instance, we combine several of them into one output so that we can actually do some number resolved detection. Yes. So then about the experiment itself. I mean, what's in the name? Quantum thermodynamics. Well, this is actually about an old problem in quantum physics. Now, how to reconcile unitary evolution with thermodynamics. These look to contradictory views of the universe. However, theory tells you that almost all global unitary evolution produces local thermal states. So quantum physics is actually compatible with the observation that if you put a thermometer in a glass of water, that it shows a real temperature. The challenge is to make this happen without, you can do the experiment, but by introducing decoherence, that's easy. We want to do it without introducing decoherence. So the experiment then looks like this. We take input photons, we inject them into a QuiX photonic processor, in which we programmed a unitary evolution mimicking the Hamiltonian evolution that we desire. And then, of course, it's a Hamiltonian system, so the single photons that we send in should come out again as a pure state. What comes out should also be a pure state. But if we locally look at the subsystem, it should look thermal. That is the thing we want to show. And this is indeed what we see. If we look at the photon distribution and one of the outputs, then you see here in the red dots the results of our single photons, following exactly the theoretical prediction, which are the black dots, and very closely the expected thermal state, which is the gray bars in the background. Whereas if we actually change the timing of the photons so that they become distinguishable, then we're actually simulating a classical system. And then we get the blue dots, which is now deviating strongly from the thermal state. And so this shows that we can actually do the experiment and show that this system follows the expected theory. So we're very happy that this works. However, this is the simple part. The difficult part is actually proving that the overall state is pure. And this is where the advantage of the big processor comes in, because we have now a part of the processor in which we can program our Hamiltonian, and then we can program in the second part of the processor another unitary evolution, which undoes the effect of the first part. So if we send in 3 photons here, they could completely scrambled by this blue U, then we can undo the scrambling with the second U, and we expect to find the 3 photons back. So we're inverting the transformation in this processor. And this actually works. So you see here on screen, if we only introduce the unitary evolution by U and then an identity matrix in the second part, then we get the thermal state that we expected there to be. But if we undo the unitary evolution from the first part by the inverse in the second part, we get back here in green exactly the 3 photons that we sent in here. They come out there. And for another check, we also looked at what happens if you do, before doing the inverse, you apply a Fourier transform to show that the photons are actually quantum interfering. So I was very happy to see these results. I mean, it really worked. It means that it works as advertised. And it's important to realize why this works so well. It works so well because we have a large phase-stable processor with a very high transmission, very low losses, and exquisite control. I mean, it's very important for this experiment that whatever you program here, that you can undo it exactly in the second half of the processor. And this was crucial for this experiment to work. Okay, if you want to read more about this, you can find this and other results in the preprints down here. I have to thank my colleagues of the group. You can see the pictures over here, and our collaborators from the Free University in Berlin. And thank you for your attention. Thank you.
Yeah, thank you very much, Pepijn, for sharing with us these nice pieces of work that you have done. Now, As the audience might figure it out very quickly by just Googling it, Pavine is one of our closest collaborators. And I don't mean it sentimentally, at least not only, but I mean it geographically. Yeah? We could almost walk with our processor in our hands, and that is here, the one that you see in here. Walk from our facilities to Pavine's lab. Then in the end, we took a car because it was raining, of course, in the Netherlands. But this gives you an idea of how compact and portable our processors are. So let's start with some questions. I think we have some time now. If you would have access to a processor with more modes, what exciting experiments would that enable you to perform?
Oh, that's a nice question. Oh, of course, there are many experiments you'd like to do, but not going to tell. But maybe in general, you can say that having a processor with which is larger and at the same time would also need more photons, then you start getting into the regime where you can do experiments that are no longer feasible to be simulated on a classical computer. And that's really the interesting future of this kind of experiments, to get into the quantum advantage regime.
Very good. And I think it's something that it's enabled by the scalability of integrated photonics
Yes.
as the platform. Very good. One reminder for the audience, keep asking questions in the chat. We are reading them live. Another question, once you have an experiment designed, how long does it take to set it up on the processor?
Very short. I mean the intellectual part of designing experiment is the hard part. Once we have designed our the Unitary that we want to program in the chip, it's a matter of minutes of programming it into the chip, and actually within a second of it will after uploading it, the chip will display the matrix that we have implemented in that.
Very
so
good.
we're never limited by the speed of the processor in our type of experiments.
And this is all enabled by the control software, the software interface
The software does it all for us.
comes
We only
with the
provide the
processor.
Unitary, and the software does the rest.
Very good. So if there are no further questions for now, let me thank you, Pavine, for joining us in the studio today. And well, I hope to see you soon, and have a safe trip back to Twente.
Thank you very much.
You're welcome. And now I think it's time for a little surprise, because I've got a note that there is someone snooping around at our facilities in Enschede. Let's have a look.
Hi, I'm Larissa, and today I'm in Enschede to have a look at QuiX Quantum. They are developing the most powerful processors in the world. That sounds interesting. Let's have a look. I think I have to be in here. Yes, hey Marcella!
Hi Vanessa, welcome at QuiX Quantum. Come on in and they are going to show you the Quantum Lab.
So before we go to the lab, maybe you can tell me something more about the company.
So QuiX Quantum is a small 3-year-old startup. We've got 13 employees. And we design and characterize and sell these photonic quantum processors that are shown in this picture behind us. There's 400 little heaters, which are behind these gold leads, on top of optical waveguides that, where the light comes in and goes out. We can do fundamental science, or we can solve problems for real companies.
So what happens before the quantum experiment?
Michiel down in the characterization lab will tell you all about it.
Okay,
Come with
let's
me.
go. Hi!
Hello.
What are you doing?
So over here we are characterizing our 20-mode photonic processor. So right now I'm measuring its reconfigurability. That means that I want to study how well I can implement the settings for the transformation of the light that I want to implement.
Okay, and what is the difference between this lab, what you're doing, and the other lab?
So in this lab we do a classical characterization, which means that we just characterize what's happening on the photonic processor. And then in the other lab we use the photonic processor for performing quantum experiments using quantum light.
What's over here? Can I have a look?
Yeah, have a look at
Yeah?
it, please.
I see red lights. What is it?
So over here we perform our visual inspection of our devices. So we inject red light on a chip, and then we can see if there's defects on the waveguides, or if there's errors or mistakes in the design. And then if everything looks good and the light goes nicely through the chip, we can select it and we can assemble it into a photonic processor. And then afterwards it goes to the other lab for the quantum experiments.
Okay. Well, so if it's perfect, it will go that way.
If it's perfect, then go to the other lab.
Okay. And what are those boxes?
These are our devices that we measure and that we then ship to customers.
This is our second lab where we do quantum mechanical experiments. Come in. This is where we actually do quantum science. And so we want to show you a little bit about how our whole system goes together, not just with our devices, but as a whole ecosystem. So in this little black device here is where our quantum dot light source is. This is where we generate individual photons to go into the chips that Michiel showed you. Because without quantum light, we're not doing quantum science.
It's not that light, right?
So this emits only a single particle of light every time we ask it to.
And what is the sound I'm hearing?
So the sound you're hearing is our refrigerator. And it's not just a normal refrigerator like everything else around here, it's the fancy version. So this fridge goes down to minus 272 degrees to keep our detectors cold. Detecting those individual particles of light is very difficult. And so we use superconducting detectors, each of which can detect a single photon with 80% probability.
So what's the point?
So if we take our quantum light source and we connect it to our quantum processor and then to our detectors, we get a quantum computer. And with that quantum processor, we can do fundamental science or we can solve problems for real companies.
Okay, well, thank you, Devin, for the tour. Let's go back to the studio.
And we are back. So I hope Larissa enjoyed the visit, and so did you guys watching from home. Now, coming back to the storyline of this webinar, we were answering the question, how is QuiX quantum technology today tracing the path to the quantum future of tomorrow? We have heard the story of Professor Pepijn Pinksé from the University of Twente in the Netherlands, and now we go a bit farther away in Germany at Paderborn University, where our academic collaborators are working with our 12-mode quantum photonic processor. And so we are at the next guest speaker. Let me read it because it's difficult. He's the group leader of the quantum network part of Christine Silberhorn Integrated Quantum Optics Group. And since 2020, is also the manager of the Interdisciplinary Institute for Photonic Quantum Systems at Paderborn University. Let's welcome Dr. Benjamin Brecht.
As Katharina said, I'm Benny Brecht from Paderborn University. I work in the Integrated Quantum Optics Group of Christine Silberhorn and at the Institute for Photonic Quantum Systems. Let me start first with a few words on our group. We are located at Paderborn. Paderborn is a small town in North Rhine-Westphalia, Germany. And as you can see from the pictures, it's a historical town, and if you are in the area, Paderborn is well worth a visit. Now, our group consists of three parts. We have the technology subgroup, which is led by Christoph Eigner, where we fabricate nonlinear optical samples. For instance, photon sources as those that Pepijn Pinksé just talked about in his talk. We then have the devices subgroup led by Harald Hermann, where we take the raw samples from the clean room and turn them into functional quantum devices. Here we focus on electro-optic modulation, packaging, pigtailing, so really build robust samples that can be used in experiments. The last part of our group is the quantum networks group, which I'm heading. Here we're doing the more abstract quantum applications, ultra-fast quantum optics, quantum walks, and the latter is also the part of the group where the work with the photonic processor happens. Before I dive into what we're actually doing, as is usual in many presentations, the presenter is not the person actually doing the work in the lab. In our case, the lab work is done by two very talented students, Federico and Philip, who are really doing great work. Now, that's the outline of the talk. In the next few minutes, I'll give you a brief introduction into quantum walks, because that's what we're focusing on with the photonic processor. Talk a bit more about how we characterize the photonic processor and make sure that it's operating as we think it should, and then show a few results on a 2-photon quantum walk on chip. Let's get started with an introduction to quantum walks. If you do not know what a quantum walk is, you probably know what a random walk is. Random walk is a mathematical construct where a walker tosses a coin at each crossing that she arrives at, and depending on the outcome of the coin toss, the walker will take a step to the left or to the right. And this pretty simple model can be used to model a lot of real-world systems, stock exchange, Brownian motion, animal movement, and so on and so on. Adding to that the notion of coherence, which means wave interference or actual true quantum interference, we end up with a quantum walk, which is now a system that allows us to model quantum mechanical systems. Examples are photosynthesis, large quantum networks, search algorithms, and most importantly, quantum walks have been shown to be also primitive for universal quantum computation. So we see that quantum walks are actually a powerful platform for quantum technologies. If you want to realize such a quantum walk, one of the most straightforward ways to do that is to build a system such as schematically shown on the slide, which is really a large interferometer made of beam splitters and phase shifters. And if you think about it, that's exactly what the photonic processor is. It's an array of controllable beam splitters and phase shifters, thus it should allow us to implement quantum walks. Right, let me now show you a schematic of our experiment. And this is really very schematic. But we start off with a laser that generates picosecond pulses with which we drive a photon pair source. For the experts, we are using a photon pair source based on KTP waveguide that generates photons at telecommunication wavelengths, and the two photons have orthogonal polarizations. While we flip the polarization of one photon, we couple them to fibers. We connect the fibers to the photonic processor, which, as you've heard, is the 12 input, 12 output version. And then we connect the output of the processor via optical fibers to superconducting detectors, where we perform our coincidence detection. Since it's all fiber coupled and it's controllable via Python, the photonic processor actually seamlessly integrated with our lab infrastructure, which made it really easy to get started. How did we characterize the chip? Well, we performed homomental interference. If you don't know what homomental interference is, then the important part here for you is that it's one of the standard measurements you have to do if you characterize photon pair sources for use in photonic quantum technologies. You will typically get a curve as shown on the slide where you do see a dip at some position. Important figure of merit is the visibility of this dip. So how close to zero do you get? And in that case, our reference measurement off chip gives a visibility of about 82%. This is the reference against which we will test the QuiX chip. In this measurement, we use two neighboring inputs of the chip and perform a homomental interference at the first beam splitter, just pipe the light through to two neighboring outputs. Let's have a look at the visibilities we get from these measurements. There we go. First of all, you will note that the shape of the dip is the same for each pair of outputs. This means that, yes, we do get quantum interference also on the photonic processor. Let's have a closer look at the visibilities. We see that over the different inputs of the chip, they vary a little bit, but each of them turns out to be at least as high as the one from our reference measurement. So we see that the photonic processor does not change or degrade the quantum interference properties. Again, for the experts, if you're wondering about the shape of the homomental interference, that was a problem with the spectral filters we used. We have upgraded the setup and now see the following dip. Which you can see has the expected nice smooth shape. This is already with the photonic processor, and we now see a visibility of 98%, which is close to ideal. Good, now we know that the photonic processor works and it does not degrade the quantum interference properties. So next we implemented a two-photon quantum walk. We take the 2 photons from our source and we send them into the photonic chip, and we realize a Hadamard quantum walk. A Hadamard quantum walk is basically the archetype of quantum walk where each beam splitter is set to a 50-50 reflection transmission ratio. So at each step, the walker has equal probability to go left or right. And since it's a quantum walker, it will actually go left and right simultaneously. We propagate this walk for 6 steps until we hit the edges of the system, and then again just pipe the light through the chip to the outputs, measure coincidences between all pairs of outputs. Let's have a look at the results we got from those measurements. First, we went to a case where the 2 photons were distinguishable. This means that we do not see this homomental interference. We essentially see 2 independent quantum walks. And the type of measurement results you get shown in the lower left, experiment versus theory. We kind of map the output of one photon, the output channel of one photon against the output channel of the other photon. And as you would expect, the 2 photons like to exit the chip in 2 separated ports. So one on the left, the other one on the far right. We do see a high similarity of about 96% between experiment and theory. We then went to the case where the 2 photons are indistinguishable. Thus, we do see quantum interference. We do see this homomental interference happening. And again, we see a high similarity between experiment and theory. And the remarkable feature that you would be looking for here is that now the photons like to cluster up. The photons like to exit the chip in the same output port. This is something we're seeing, and this is something that again confirms that, yes, we do see an actual 2-photon quantum walk, including full quantum interference on that system. The best thing about the chip for us is the reduction in measurement time. We've done similar experiments before, and anyone who's done those experiments in typical standard bulk setup knows that to get such a correlation matrix, you typically measure for days. It involves plugging in and out a lot of fibers, moving a lot of couplings. It's pretty cumbersome. With the chip, we could reduce that to a few hours, to maybe 3 hours at most. By now, we're actually well below an hour. With that, let me now come to an outlook of the next steps. We've seen the systems working. Now, the next steps we want to pursue is study the behavior of entanglement during quantum walks, look at more complicated quantum walk topologies, study effects of noise and random errors. Since the measurement times are so low now, we can actually measure many configurations of different noise patterns, which we wouldn't have been able to do before. Some publication with first results, and some of those, especially on the entanglement during quantum walks, is currently in preparation. Well, that's it. All that's left for me at that point is thank you for your attention, to thank our funding agencies, all the members of our group, and QuiX for supplying the photonic processor that we're using to do these experiments. Thank you very much.
Thank you, Benjamin. That's really great. Very interesting results, and it's great to see how high degree of control and reconfigurability is really key to for enabling such a complex experiment. Now we have some time for some questions. So let me shoot the first one. If you had more detectors, so that you could monitor all the outputs, how would that improve your experiments?
If we could monitor all the outputs at once, we would essentially gain another 1 to 2 orders of magnitude in measurement time. So we could reduce measurement times down from about an hour to, say, less than a minute.
Wow, that will make happy a lot the students working in the lab.
Oh, yes.
And now I'm speaking to all the physicists in the audience. We can all relate to that. Very good. Next question. How can you implement more complicated topologies on a planar chip?
If you want to do that, you can use a method that's called a split-step quantum walk, where essentially you sacrifice circuit depth in favor of more complicated topologies. So you could take two subsequent beam splitters and treat them as one step in your quantum walk. And with a system like that, you could implement things that are called, say, Levy flights or quantum walks in a circle.
Very good. And next question, I see it coming. Are you planning to use more inputs?
We are planning to use more inputs, and at the same time, we're also planning to use more photons. As Pepijn Pinske said earlier, if you want to scale the systems, well, you have to increase the number of modes and the number of photons. We're planning to do both over the coming years.
Very good, excellent. So there are no further questions for now. So Benjamin, thanks a lot for joining us online. And it was a great pleasure to have you. And now we are ready to move on. And back to the studio. I don't want to waste more time now because it's the moment that we were all waiting for. Ladies and gentlemen, the 20-mode quantum photonic processor. Jorn, take it away.
Thank you. Thank you very much. So today I have indeed the honor to present on behalf of the QuiX team our newest product, the 20-mode quantum photonic processor. But before we start, let's first have a look at the experiments about the quantum advantage using photons. It is really an impressive and great, and I would even say beautiful experiment, where here quantum advantage was achieved using photons and using over 100 modes, each interfering in the middle there at this picture at a beam splitter, and you see all the bulk linear optics that was used. Yeah. But the question is, how can we make it more scalable, and also how can we make it programmable? And that's why we at QuiX use the quantum photonic processor. It's the processing unit for a photonic quantum computing device. It is based on integrated photonics, and in it the light can interfere, as we've seen before in the talks of our guest speakers, and it can be programmed. So we have an input quantum state of light that is injected into the circuit. It performs a computation there, and the result afterwards is measured, as also the guest speakers before already mentioned, by measuring the outputs. And this we all put in a plug-and-play box, the quantum photonic processor. But first, let's have a brief review at the key features of the photonic processor. So what is clear is that large number of modes will enable more complex calculations, and the computational power gets higher. And since we're dealing with photon states and single photons, it's important that it is very low loss, the lowest loss that you can get, because every photon that you lose will lose information in your process. And what's very important is when you program it that you can do this with a high fidelity, because a high fidelity means that you exactly know that what you program is also what you get. And we also use the strength of integrated photonics, namely the inherent phase stability of a chip. And also the question we ask ourselves, of course, with the 20-mode photonic processor, will it also preserve the quantum state of light as nicely as has been shown already by Benny in the presentation before? So first, let's have a look at the unit cell of which this processor consists. It has two tuning elements. The first one tunes a tunable beam splitter that controls the amplitude of light, and the second one tuning the phase of the light. But now we want to scale it up from 12 modes to 20 modes. And in order to let you show what task we gave ourselves in order to achieve this, let me show you the full functional designs with all the waveguides that guide the light on it. And you see that this is what we at the QuiX team actually achieved. So we have 20 input modes and 20 possible layers of interaction with in total 190 of such unit cells that we made and 380 tunable elements, which I think also makes it one of the most complex photonics chips there is. And first, let me show you a picture of the chip that we used. And it looks like this. It is approximately 2.5 by 2.5 centimeter big, but this is not yet accessible. So we made it accessible using fibers and electronic wire bonding. And this is really the heart of our processor, the 20-mode quantum photonic processor available at QuiX. And we are proud to say that this is the world's most powerful quantum photonic processor that is around. But at QuiX, our ambition does not stop here. What we want to achieve with this processor is we want to also deliver it at our customers in a plug-and-play fashion and measure it in the lab. And it needs to be programmable. And you would think that such a complex device is really difficult to program, but actually it's not. Because we made the software to make it easy. You just simply dial up our QuiX software, and within a few lines of code, you can already program your processor, making it really easy and to get to quantum photonic experiments within a second. So let's have a look at the first test that we did. So how did we test it? How did we validate that this device works? And here's the good thing of using linear optics. To characterize it, we can use classical laser light. We started with a 50-50 nanometer laser, a fiber switch to go through all the 20 ports and detected all the outputs at the end. And using our QuiX software, everything was completely and fully integrated. And you can go on measuring the whole day. And now let's already have a look at the first results of our silicon nitride chip, which is one of our big benchmarks. What are the losses? And you can see a picture of this chip and the red light nicely propagating through it on the right. And we are happy to say that using the triplex technology supplied by Lionics, we achieved losses below 3 dB on average, so 2.9 dB we have on average, with very low fluctuations over all the 20 ports. So this is really a great result. And the next thing that we said we will have a look at is its programmability. So how do we actually tune such a quantum photonic processor? And what you can see here in this video on the right is where you have a certain set of input modes and output modes. And what we're doing here, we start at the untuned photonic processor and slightly going through every single beam splitter to make a nice propagation. And we really see here how it goes from chaos to order by tuning it 1 to 1. So, but when you program it, it is of course important, as we said, that what's the fidelity? So the figure of merit here is the fidelity. How close is what you actually program, what you set, to what you get, what you measure in the end? And we've done this for the first set of matrices, what we call diagonal and anti-diagonal, and we get to extremely high fidelity, as high as 99.85%. But you want to, of course, note if this is true for many of such matrices. So we had to look at many different measurements, and what you see here are actually 190 measurements we performed, all very fast and automated. And what's actually the fidelity? How good can you tune the tunable beam splitters on a chip? We see that on average, we are at a fidelity here of 99.5%, which is, which is extremely high. But next, this was only using the tunable beam splitters, but it's also, of course, for quantum photonics experiments important to tune the phase of the light, to really have full control of the light. And this would then use twice the number of phase shifters. And our benchmark for phase-sensitive measurements here were the Haar random matrices, where you can see an example on the left-hand side. And while these pictures look very chaotic, but they look very much the same. And the question is here, so how good can we program those? And then let's have a look at the fidelity on the right-hand side. So the fidelity here, when we compare to the 12-mode processor, where we also measured a set of 1,000 Haar random matrices, we see that we increased the fidelity of our processor from to 97% on average. And this at the same time while increasing the number of modes and also more than 2 times the number of tuning elements. When we now know that we really nicely can tune our processor with classical light, the question is, how does it do this with quantum light sources? So, as already Benny said before in his talk, it is very important that you get a good visibility and that the quantum state of light is preserved. And this is done doing homuncal measurements. And we did that for our processor at the labs at the University of Twente with the photon source that was already mentioned in the earlier talk. And we measured that for every single unit cell in our processor. And let's see what was the visibility. So again, here the visibility is very high. So the dip goes down nearly to 0. And we see that on average, for all the beam splitters, we get an average visibility of 98%, which is close to perfect. So we can safely assume that the quantum interference using our photonic processor is preserved, and that is very useful for quantum photonic experiments. So let's go to the summary. What I've presented you now is the 20-mode quantum photonic processor, the world's most powerful quantum photonic processor. And what you might be able to read here is how we increased from more than 1 year ago with the 12-mode processor webinar to now. And we decreased, we increased the number of modes almost 2 times, while at the same time decreasing the losses from 5 dB in total to less than 3 dB. And also the fidelity. We have more than 2 times the number of tunable elements, but at the same time, we improved the fidelity, how well we can program our processor to 97%. And all this while maintaining the turnkey accessibility of our processor. We can ship it around the globe and install it very easily in a customer at a customer site. And this is something we are really proud of, that this is a plug-and-play product. So what's more? So if you want to have more information, we will send to you our archive paper that is in progress after this webinar. And as Jelmer Renema already mentioned, if you want to have a custom device or something adapted, you want to work with us, write us an email at info@quixquantum.com, and we are happy to discuss with you future projects. But what are we planning more in the future? One thing that we want to achieve in the future is to have cloud access to our processors. You already have seen how easy it is to simply using Python to use our processor, and we want to make this accessible via the cloud, and then you can use all the equipment in our labs remotely. But also at 20 modes, that's for us not the end of the road. And I'm happy to say that this picture of our 52 mode prototype is not a render, but is actually what we have produced and which is currently under investigation. And with that, I would like to thank you, and we are happy to answer your questions.
Thank you very much, Jorn. That was a very nice presentation of the technological development that we have achieved in the past year. So we have some time now for answering all your questions, hopefully. And let's start with the first one. Now, where is the discrepancy in insertion loss and fiber coupling loss coming from? How can insertion loss be further improved?
Yeah. So I think that what you've seen, that a big chunk of the losses that we have now are indeed the fiber coupling losses. And this is something we want to improve, and this will greatly improve our product. Also for the users, because every photon they struggle to generate in the lab, they want to measure at the end, right?
Absolutely. So improving for the technical people, mode matching at the facet, that would solve the problem. So very good. And for which, another question, for which wavelengths can you make devices?
Yeah, that's a good question. So the transparency window of silicon nitride goes from 400 nanometer to 2.5 micron, right? And as Jelmer already mentioned, we are now currently measuring the first devices for 925 nanometers. And this step, I have to say, we think went really well. So that's something that will come up in the future. And I think also something that we can be proud of. But we can adapt it to other wavelengths as well. Yeah, so
there's a wide
as
wide
long as
range
it's transparent,
of
we are happy to supply you with the processor.
Exactly. Very good. So another question. Fidelity went up with more channels. Do you expect this to continue? Is this processor better for 12 by 12 than the previous one?
Also, that I would say is a really good question.
That's a
right?
good. That's a very good question indeed. I think they mean on the submatrix.
Yeah.
Right? Yeah.
Oh, so you mean?
I think because is the processor better for a 12 by 12 than the previous one? So the previous one was indeed a 12 by 12, and now we have a 20 by 20. And what's the fidelity for a submatrix?
Yeah, we can come back to that. I have to look it up. We've done that experiment, but I don't know it.
I can add. Right? It looks pretty good, as much as the 20 by 20.
And in general, fidelities on subsystems are larger than the fidelities on the complete system. So you would expect, given that this processor has a higher fidelity already on the 20 by 20 system, if you go to a submatrix, you expect that it has an even higher fidelity there.
Yeah. One question for you, Jelmer, actually. So someone noticed that the NISQ quantum chip with quantum light sources is also available for QuiX. When can we purchase this kind of chips?
Yeah, so I think that's referring to our near-term photonic quantum computing system, which is on offer right now. So info@quixquantum.com, you can apply for a quote.
Very good, and we'll get back to you. Another question. Will the 50 by 50 also run at 1550, or is that related to changing the 925 nanometer wavelength? With the smaller wavelength, I expect you can scale up easier. Oh, that's a technical question.
Yeah, it's a fair question. So the 52 mode processor we only dared to use with existing building blocks, right? That we have right now. So our Lego pieces with which we can puzzle together a 52 mode processor. And for that, we settled for the 1550 nanometer approach, because this is what we have most experience in, what is most developed. But we also made the transition indeed to 900 nanometers. And there, the footprint is at this point roughly the same. But there, the devil is really in the details, and I'm happy to discuss this with whoever ask that question offline. So I would say write us an email.
Very
happy
good.
to discuss.
Great. And maybe now for the potential customers in the audience, because they have seen, we have given, we have supplied our collaborators with 12-mode processor. We have shipped it through Europe. How actually work the installation of these systems?
The answer is good. It works really good, right? No, and that's I already mentioned that I'm really proud that from chips, we really went to a plug-and-play product that you can put in a crate, you ship it around the globe, and with the Zoom conference, for example, if in the times of the pandemic, right, we couldn't send a technician, but it really went exceptionally well. Basically, setting it up, plugging it in, running the program, and then most of the time is actually connecting the fibers, simply, as you have to do that, and learning the programming language, right?
Yeah.
It's as simple as that. So typically half a day, you have it up and running in your lab.
To do great quantum experiment. One last question I see, question concerning the QuiX roadmap. Do you plan a universal quantum computer? What kind of software access are you planning for the future?
So yes, we are planning universal quantum computation with photonics, as I mentioned, in 2026. Software access, this will be something, let's say, quite comparable to what is out there for other quantum computing platforms. So where we try to virtualize away many of the details of the system, but where the user provides input on, let's say, a functional level. So in our case, that would mean that you say how many photons you want at the input, you say what kind of optical transformation you want, you say something about the detection. This all goes into a pipeline, into a queuing system, and when it's your turn, that experiment is run and you get the answers back. So that is what we mean when we say cloud access.
Very clear, very clear. Okay, I think there are no further questions. So, well, we made it. We are at the end of the day, and what a day, ladies and gentlemen. We have shown you the most powerful processor in the world, and we have learned so many things. Who is QuiX? The market leader in quantum photonic technology. Why QuiX? Because it's mature and reliable technology. What QuiX can do for you? Well, providing you with low loss and fully reconfigurable quantum photonic processor. And how QuiX Quantum is today building the quantum future with turnkey systems for photonic quantum applications. So now, the round of thanks, of big thanks. First of all our guest speakers, Pepijn joining here in the studio, now on the road towards Enschede, Benjamin. Hi, Benjamin. Online from Paderborn University. You, everyone watching from home, thanks a lot for joining us. And my last thanks goes to our engineers watching from home. Thank you guys for bringing home this nice piece of work. This was QuiX Quantum, the fastest way to a quantum future. Thank you very much.